Hey everybody, good evening and welcome to N-Simplex Pachinko. This is Obi-Wan Pez. How's everybody doing tonight? Been a little while. Amazing. Oh, that's good. Great weight was lifted off my shoulders. Megalomorph! Good evening. For anybody who is not aware, um, Megalomorph is one of our other uh, math streamers and does a great job, especially with stuff that is over my head. So, welcome in. Good evening. Hoo. Nice. Operation Tango. I don't think I've played that one. Alright. So, this evening we're just going to play around with some... to start with. We're going to play around with some, like, Christmas math. Some of it is just going to be Christmas themed. But there is at least one that we can start with. And this is kind of a classic problem. You've probably seen it before, and you probably know the answer if you've done it, but nonetheless. So how many gifts are actually given in... I have seen that one before, yes. 31 oct is equal to 25 deck. That's that. We might actually want to look at that one earlier. Alright, look at this one later. It's, I mean, I might even go further. Why, thank you. Right, so in the 12 Days of Christmas, this might be a little bit more of an English sort of thing, true. Um, in the 12 Days of Christmas, there are, again, a... partridge in a pear tree, 2 turtle doves, 3 French hens, and 3 French. And now that I'm doing it in the opposite direction, this is much harder. Yeah, I never remember what the actual things are, but I'm gonna look that up real fast. There we go. Saw some other one in here that was like for collie birds, C-O-L-L-Y. So I don't know about that one. But yeah, so this is a well-known mathematical type problem where if you're thinking about this in terms of the ridiculous type of thing that would have to happen, where every single day on, uh, day one, you get a partridge and a pear tree. On day two, you get two turtle doves and a partridge and a pear tree. On day three, you get three French hens, two turtle doves, and a partridge and a pear tree. So this gets, right, this starts building further and further out as you keep going, which means that on, again, day 12, you get these 12 things, the drummer is drumming, but also all of the other things above it. In the case of people, I believe that means that their skills are being used here. Renting them out for the day. Right, so if we look at this, and Super Brain, you're going to slap your head in about 1 minute. Right, this is a partridge and a pear tree. And on day two, you get yeah, I'm not sure about the friction caused by air resistance heating up the planet, but if it is a significant contributor to global warming, we may have to have a chat. All right. On day two, you get the partridge in a pear tree, but then you also get the two turtle doves. On day three, you get the French hens and two turtle doves and three French hens. Oh, you know me so well. It's not technically Pascal's triangle because we're not adding up the things that are coming with it. However, the structure is here, right? This is essentially right. We've got this three-dimensional shape here, which is again going to be built up as a three simplex. Right, so the number of gifts on any given one day is nice and easy to calculate. So that's going to be so I don't know that they're regifted, or maybe that's what it's supposed to be, but right, on the nth day you're looking at the summation of all of the n integer values before it. Yeah, there you go. Well, sort of. All right, nope. Let's go back here. There we go. Good. Right, so indexing from 1 to n, we're just adding up whatever the index is for all of those individual values, which is, again, going to just be n times n plus 1 over 2. So this was the Gauss formula that we get there. Yeah, I mean, it's hard to remember all the random formulas that are out there, but the easy way to really look at this is say, like, okay, if you have something that's like a fourth day, yeah, it's okay. Oops. So one of the favorite things for mathematicians to do here, and this is kind of what Gauss did when he was doing this, was saying, okay, we're going to bump this out and put the 1, 2, that's not it. A. Extend this one. There we go. So 1, 2, 3, 4. Fourth row here. And then start building it out. So now we get a nice parallelogram, and now you can multiply just base times height in order to get it. And because this is a taxicab type problem rather than like actual distances, this is just going to be like the height is the same as the slant height, right? We could just kind of tilt it back over, and now it's a rectangle. So this is going to be n plus 1 rows. Yeah. And n columns. And we only wanted half as many things because now we've got 2 triangles. Yep, so this is the same thing as the Gaussian stuff. So that's what you get for any given day. And then you've got to think about what about the sums of all of the days. So we're going to add up all of these. Well, it turns out that these are triangular numbers. So if you want to, you can come up with like, okay, what's the... I mean, I could come up with it. It's just, I thought it would be easier to search for it. Oh, silly me. It's literally just that. Okay. No, wait. Sorry. Sum of... Oh, man. I'm doing fine. I promise. Okay, nice. Okay, so we can get the sum of all of these. These being 1, 3, yeah, 6, 10, 15, etc. Right, so the individual... Man, I'm having a day. All right. Okay, so some of the individual triangular numbers. We're going to... mathematical problem solving. Nice. Alright, this is n squared plus n all over 2. And if we want the sum of all gifts up to that particular day, it's going to be I goes from 1 to n again. And this time we go with I squared plus I all over 2. And with this one, we can say, okay, if we do this, then this is the same as 1/2 the sum I goes from 1 to n of I squared, plus 1/2 the sum as I goes from 1 to n of just I. This is going to be, again, the same thing that we just found down here. Well, half of that, anyway. This one here, our I squareds, end up being a bit different of a formula, which we can work out through induction, but ends up being n plus 1, 2n plus 1 over 6. And then plus, this is just the same thing again, 1/2 of n squared plus n all over 2. Uh-oh. Alright, screwed it up. Where'd I screw it up? Not surprising, quite honestly. The 2m minus 1. Okay. So that was from memory, so quite possibly it's wrong. We'll check it. So anyway, you can do this one through induction. And if it's correct, if that is correct, then we're going to say, all right, this is going to be 1, then 4, and then 4 plus 6 is 10. 10 plus 10 is going to be 20. And then we'll get 35 after that. So in theory, let's just check these real quick to make sure we've got all of them, because otherwise that's going to be really embarrassing. So this is n equals sum 1, 2, 3, and 4. Okay, so 1 is going to make this 1 times 2 is 2, times 3 is going to be 6, divided by 6 is 6. Okay, well that's good anyway. 2 is going to be 2 times 3 is 6, so that eliminates there. And 2 times 2 is going to be 4 plus 1 is 5. Nuts. Okay, well that didn't work. Oh, hang on. No, no. Okay. I'm checking against the wrong numbers. Boy. Alright, n sum of n squareds. Let's try that. That's not really what I want. I squareds. Okay, so squareds are going to be 1, 4, 9, 16. So then we're going to get 1, 5. Okay, good. This is correct then. For 5. Plus 9 is 14, plus 16 is 30. Alright, so this is going to be the sum of the triangular numbers. Oh, I guess. Oh, I forgot my other tag. Hang on. There you go. Superbrain always likes that one. Alright, another 2 that we have here. Yeah. Okay, that's going to be over 3. Okay, because that whole thing's going to be gone now. This is 2n plus 1. 2n plus 1. Oops, yep, yep, yep. Yeah, I just saw that. So yeah, that's going to be plus 3. It's going to shift over there. It's going to be 2n plus 4 all over 3. Pull another 2 out of here. Oi. It's going to eliminate there. So n plus 1. Sorry, I went like halfway, Matthew, and then I just kind of ducked out. It's alright. N plus 1 over 3 again. That's not n plus 1, that's n plus 2. One of these days. I don't know why I'm going over it again. I should just erase it and just start over. Okay. n plus 1, n plus 2, which is really what people want out of the perfect squares. The sum of the squares is they want to do this pattern where it's just like, oh, the regular numbers were just n and n plus 1 over 2. So that means that we should do n times n plus 1 times n plus 2. Should be the next number. Well, it turns out that's the triangular numbers. That's not, it's not the sum of just the perfect squares. All right, so the sum of the perfect squares ends up getting you this thing. And again, you could just run through it real quick to make sure. 3, 4, and 7, right? 3 times 4 times 7. 3 times 2, so 2 times 7 is left over is 14. Okay, I'm convinced enough that I didn't screw this up. But if you want to prove that this is actually the formula for it, right? The sum of I going from 1 to n of I squared is n plus 1, 2n plus 1 all over 6. Naturally, you should not be like just saying, yeah, that's fine. You should at some point, you know, being good scientists, mathematicians, what have you, should be like, okay, let's look for evidence of this. And if you just see a list of numbers that end up coming out to be exactly the same amount, that's nice. It doesn't prove it. Right. So yeah, I know Graham and Nuth from, you know, other stuff. Patashnik, I haven't actually heard of really besides this particular book, Concrete Mathematics. And I really need to pull that from the library. Still haven't done it. I mean, if it's going to help your research. Anyway, so in order to prove this, the easiest method, or really best method, I guess, to do this is going to be like, well, do what's called induction. So we show that n equals 1 yields a true statement. Assume n will work generally. And then third, if you can extend it just one more step and say, oh, well, if it worked for 1 and it we're just assuming for the moment that it's going to work generally for n. Then we have to prove, starting from n, that we can get to n plus 1 just by using standard mathematical, algebraic manipulation. If you can do that, then you've just shown that it works for 1, and therefore, since it works for 1, it works for 2. And then therefore, since it works for 2, it has to work for 3. Since it works for 3, it has to work for 4. And that just goes on ad infinitum as far as you want to go. Yes, induction is such a beautiful thing when you can get it to work. There are some things where it's just like that's not the method to prove it, and it's so unfortunate because I'd really like to be able to just, or induction is too hard for this particular type of problem, that kind of thing. Okay, so 1 again was that show that n equals 1 yields a true statement. So the sum of I going from 1 to 1 of I squared is equal to 1 squared. Right? Equals 1. Cool. Is equal to 1 times 1 plus 1 times 2 times 1 plus 1 all over 6. Which I'd already mentioned before, but yeah. Right? This is just going to be 1 times 2 times 3 all over 6, which is 1. Okay, cool. So to assume true for general n and 3, prove n plus 1 is true. So this is the slightly harder part. So for this, we say that we do know for a fact that I equals 1 to n. Sorry. I is going from 1 to n. We're finding the sum of I squared, which is then going to be 1 plus 2. Nope. 1 squared plus 2 squared plus etc. all the way out to n minus 1 parentheses squared plus n squared. Okay. We've shown that or we're assuming that this is going to be true generally. And then therefore this is equal to n plus 1 2n plus 1 all over 6. All right, so then we have to prove that it's going to work for n plus 1. So what we're going to do is add on both sides of this equation here, n plus 1 parentheses squared. All right, so with that, we then have Bertrand. Thank you very much for. I gotta change the colors on that. Thank you for the follow. Did you guys hear the? Is there music that goes along with it? I hope. Yes. So that it was a song, right? That music is from Math Man, which was from Square One TV back in the 80s. That was like one of my big inspirations for, yeah. So Bertram, thank you very much for the follow. That particular music is from, Square One TV, which was like my big inspiration to get into mathematics. Basically, my mom was home most days when I was really young. Due to the fact that we had, 2 kids, it was kind of hard to, and not a whole lot of opportunity for daycare. So she stayed home with me until I went off to school, and then my brother went off to school. And gosh, from her I learned how to play chess. She wasn't very good at it. Neither was I. In fact, I'm not really still. I just know all the rules. Um, yeah. Ranking 15,000. It's probably worse. But anyway, yeah. So that was one of the things that like always came on TV. I don't know, 3 o'clock, something like that. It was a half-hour television program from PBS, our public broadcasting system here in the United States. So it was like one thing that she was absolutely adamant, you're definitely going to be allowed to watch this. Okay, so on the left, we're adding parentheses n plus 1 squared because we want to have what happens when we do n plus 1, like the sum of I going from 1 to n plus 1 of I squared. So then that's going to be this 1 squared plus 2 squared plus all the way out to n squared plus parentheses n plus 1 squared. Yeah. Then on the other side, we have to show that this actually fits into the mold that we've built here. So this is going to make n times n plus 1 times 2n plus 2n plus 1. Okay, plus, and let's do it as a separate one. Over 6 is going to be 6 parentheses n plus 1 squared over 6. Right, common denominators and all that stuff. So you can knock the denominator out to the other side and put a 6 on in front of the other one if you want. It doesn't really matter. We'll figure it out. But easy enough. Just put this in. All right. Left side is going to stay the same. Don't care. On the right, we need to combine these things. So we're going to have to multiply everything out and then refactor. So this is going to be 2n cubed. Actually, you know what? Let's not. Let's use a little bit more brain power here. So we have an n plus 1 squared on the right side and an n plus 1 right here on the left term. So let's factor out an n plus 1. That leaves us with an n times 2n plus, I keep doing that, 2n plus 1 plus 6 times n plus 1. All right, all that's divided by 6. Okay. I don't think I know that reference. All right, here we have a 2n squared plus n plus 6n plus 1. Nope, that's a 6. Dope. I can believe it. There's a lot of flashy lights and whatnot. It's always a positive. Okay. So then all of this was over 6 again. And now you notice in here we have a quadratic. This quadratic is 2n squared plus 7n plus 6. We can factor this. This is a AC 12. So 1 times 12, 2 times 6, 3 times 4. Sign of the larger number is positive. And signs have to be the same. So make those positive as well. The only one that adds up to 7 is going to be 3 and 4. Split the middle term. 2n squared plus 3n plus 4n plus 6. First group, take an n, leaving 2n plus 3. Second group, take a 2, leaving a 2n plus 3. And these have the same thing in them, so take it out. That's going to be an n plus... n plus 2 left over with a 2n plus 3 factored out. So that's going to be n plus 1 times n plus 2 times 2n plus 3 all over 6. It's possible I've seen it, but I can't think of it offhand. It's probably one of those like Mythologer things that I watched, 6 years ago or something. Anyway, there's something important to note here, is that these things now can take the form of our originals, right? The first one was n, and now it's n plus 1. Our second one is n plus 2. It used to be n plus 1. Well, this is the same as n plus 1 plus 1. And 2n plus 3, if we factor out, if we take 2 of this from 3, and then factor 2 out of the 2n plus 2, that might be a little ridiculous. Let's just write it. So I'm going to make 2n plus 3 equal 2n plus 2 plus 1, and then factor out from here, I'm going to get 2 parentheses n plus 1 plus 1 all over 6. And now we've taken this and looked at it. Oh, do I need to allow? Maybe. I don't think that's a command. I mean, it's a command, but I don't think it's my stream's command anymore, or whatever. Yep, that didn't work. Cool. Maybe. It's quite possibly. It's not gonna. Nope. Okay. Oh, punk. Huh. All right. I wish I had a better grasp on stream elements to. Let's see. URL. Nope. It seems that that's not a thing. Like, I know it's a thing. It's new command from template. Let's see. Sure, or you can post it in your Discord. Whichever. So yeah, Matthew, sorry. This is everything, right? Because we've just shown that we've taken, like, it's sort of like doing function notation, where we've taken our function, which was on just n, and now we've changed it so that our function is now on n plus 1. But we did that from starting with nothing, or starting with the n portion. maa.org, nice. Woo! All right, thank you. Yeah, okay. Yeah, that makes a lot more sense. Nice. Sure, bring it on. Okay. While Bertram is typing that out, we'll just finish this one up real quick in terms of like processing stuff. Anyway, when we show this, we're showing that now the sum as I goes from 1 to n plus 1 of I squared can now be redirected as this thing, which tells us that, yeah, the original one was true. So you have to have the correct equation, right? So in theory, you're going through all of the steps. You're not just saying like, oh well, it's gonna be like it works for just the first one where I equals or n equals 1 and that's it. Because well, it wouldn't have worked on this group of numbers, right? It still got us 1 for the first one, but then 4 broke because it needs to be 5. So when I did that and I saw I was getting 5, I got worried because I forgot I wasn't doing the sum of the triangular numbers. I was just doing the sum of the squares. So in theory, what you're doing is you've got a scientific words, right? I've got a theory as far as what this pattern is going to be, i.e., the pattern I've got is working for all of the data points that I have so far. And now I just want to generalize and get an explicit form for it so that it'll work for any number that I care to put in. So again, this is going out as far as we care to go. The data points are showing that like, other people have done this. It's working, it's good, it's fine. But we want something that's going to just do like 1,000 and without having to actually work down to 1,000. So this is more or less an implicit format over here where we're saying, okay, I'm adding the next perfect square and the next perfect square and the next perfect square. It takes forever. So I want an explicit form, which is going to get me just what's the 1,000th step. So again, it works. It has been working for all the other mathematicians who have come before us, but now we just want to prove that yes, this is absolutely it, and it will always work. Okay. So Bertram, let's see. F inverse of x, nope, of y is equal to y minus 4 over 8y plus 2, like this. That's all right. Parentheses are a big help. Oh, okay. I'm not too worried about which variable you're using because, actually, this is a point. Because if f inverse of y is equal to this, then f inverse of x is equal to x minus 4 divided by 8x plus 2. Right? Same thing. Oh, I see. You want the inverse. You have the function. Correct? Yeah. Okay. So, what do you know about inverse functions so far? I'm going to be a bit of a pain here because this is like part of my actual curriculum. I do know how to teach it. Okay, so that's an option, is to basically go the other way and say, I'm going to go here and then solve for y, right? I don't actually use that. I don't like it, which is always possible, right? You could do it, and your teacher probably wants that from you. But if we're looking at mathematical rigor, so I generally teach pre-calculus pretty much every semester. And then I have a smattering of other classes that I've been able to teach. At our 2 year college, most of us teach developmental at some point during the year, like 1 or 2 sections. A lot of people just stack it up in one semester and then get it over with. Or they do it like, 2 sections of the same thing so that they don't have to think too hard about, like, multiple preps and stuff like that. But I also do either Calc 1 or 2. I've This last semester I just got into Calc 2 again. It's been 10 years since I taught it. It's been interesting. Once we get to Taylor series, that's always the most fun. And my I hesitate to say specialty around around you, who probably knows the subject better than I do, but nonetheless, um, my my specialty in terms of teaching is differential equations. So yeah, yeah, and it's really good that you're getting it not like solid now. Okay, so one of the ways to do this is you say, okay, I'm going to trade and get y here, x minus 4 over 8x plus 2. And then we're going to do this whole x equals y minus 4 over 8y plus 2. Now, like I said, I don't really go for that. I don't like it so much because it's, for some people, for people who are confused about this to begin with, this seems arbitrary. Like, why would I do that? Um, so we have this box, and everybody's probably seen the box diagrams, and it's really annoying, I'm sure, when you don't, again, when you're not 100% on what this means. But here you have all of your inputs, and here you have all of your outputs. And F is the thing which takes all of the stuff that's valid, at least, from your inputs and feeds it into your outputs. So it'll get you all sorts of stuff. Again, rational function like this, you can plug practically any number in that you want, practically, into your input, and you will get some sort of output back. What we want is now to take something from the output, feed it backwards through this machine, and get something back from the input. And this is what we call F inverse. So rather than doing this, what I'm going to do is say, well, let's actually solve for let's solve for x in this function f of x. You could also trade it back for y. Oh, okay. Yeah, I took ODE. I have taken ODE in some form or another. I have never repeated a class, never repeated one of these classes, but I have taken ODE 3 separate times. And then I did PDE, and then I did nonlinear. All right, so the preferred method that I have of solving this is to say, okay, we're going to take that function up there, and instead of swapping out the variables, we're going to solve for the opposite variable. So take y equals. Now the question is, should I actually do your homework problem? And the answer is, I don't think so. So I'm going to be a pain in the reader. All right, I'm going to do g. G of x is 7x minus 3 over 4x plus 1. Apologies, but I'm just going to be a pain. It'll be a good check for you. Okay, so the preferred method of solution that I have is to take this, yeah, I know, and say, okay, we're going to do 7x minus 3 divided by 4x plus 1, and we're going to solve for x. So we're going to multiply both sides by 4x plus 1 to get rid of the fraction that's on both sides. Because that's just in the way, it's not convenient. Let's move it. So this ends up dividing out here. We get 1s for both of these, and then we get 7x minus 3 left over here. On the left-hand side, let's multiply in the y. So distribute, we get 4xy plus y. Since we're solving for x specifically, now we need to get these x terms together. So we're going to subtract 7x from both sides. And here this y is no longer useful to these x's. So let's move it out of the way as well. This is one of the other weird things that I do that I've developed over the past 15-ish years, is that whenever I'm doing like, oh, add this to both sides or subtract this from both sides, I always make it into an equation and then add the system of equations. So anyway, so this 7x and negative 7x add to 0, this y and negative y add to 0. Over here we get a 4xy minus 7x. Yes, you could factor out if you wanted to. And here we get a negative y minus 3. Factor out the x. We get 4y minus 7 is equal to, here I'd say negative parentheses y plus 3. I mean, yes. But also, and this is another thing, my class doesn't do matrices. Oh, I have thoughts about that, but anyway. All right, and then we're solving for x, so divide both sides by 4y minus 7. And on the left, these divide out to become 1s each. And we get x is equal to negative y plus 3 up top and 4y minus 7 on the bottom. Now, you might think at this moment, oh, I'll just swap these around again. Again, trading x's for y's. But again, it's arbitrary. Why would you do that? So, the thing to really recognize is that our g function, which is the same as the f function in terms of like it takes stuff and plugs stuff in, our g function is taking values from the inputs x and plugging them into g and getting outputs, which we called y. Okay, so here we had our x's were again input and y were output. No, I mean, don't get me wrong. You can do that, right? Oh. Do you mean matrices? Sorry. I'm like half paying attention to the conversation. So you can, if you're talking to me, Superbrain, you can swap x's for y's. That's fine. It's a shortcut. It's a convenient little trick. I don't like it because, again, students look at it and they go, okay, I guess. But the students who are going to go into math or the students who are going to go into one of the sciences should probably see a little bit more rigor in what they're doing. So what I like to do is I say, now look, X X was the input for G, but X is the output for G inverse. And Y is the input for G inverse as a function. So X is G inverse of Y. Now again, this isn't like something that you absolutely would have to do if you were teaching this, but I find it like, again, it gives it a little more structure, and it says like, this is what we're really doing. You're not going to take all these little shortcuts. It might take longer, but I think it's worth it. Now, G inverse of Y is equal to this thing. But. Right, it doesn't change anything about the math, but some of the students are just like, okay, I can just do whatever. But here, right here, look what I can do. I could say that this is G inverse of anything I want, and it's equal to negative anything I want plus 3 divided by 4 times that same thing minus 7. So I can fill that in with whatever. I could put A. I could put M. I could put poop emoji or star. Or if I'm feeling particularly pedantic, or, not pedantic, but if I'm feeling particularly relevant to this particular topic, I could put X. It didn't matter what I put there, right? I could make it whatever I wanted as long as that was the input to this particular function. Well, now I put X in there, and guess what? Now it's equivalent to what you said earlier, just swapping the X's and Y's. But it isn't just swapping the X's and Y's, it's changing with... Maybe. But the fact is, I like it. Killer King, good evening. Well, you should come in with questions, then it'll be something you're reaching for. All right, so anyway, I'm being a pain in the rear, right? But this is the point, is that what we're really doing is we're saying, okay, we're swapping these inputs for outputs. The thing that was actually an output for G inverse, we decided to make it the input of just a function, because G inverse is a function. And this allows us to standardize it and say, okay, now we'll put it on the same set of axes. So we're going to have our xy like this. If we do G, then that's going to be, some one-to-one function that looks like this. And if we do G, if we do G inverse of Y, then actually this gets us the exact same thing. Right? It literally writes the exact same thing, as long as it's a one-to-one function. But if we specifically write nope. About Yeah, more like that. This is G inverse of X. Right, so that's G of X, which is going to be equivalent, again, to G inverse of Y. But if you then decide, okay, I'm going to do a variable shift, I'm going to turn that into G inverse of X, and now it gets us this separate thing, which is now the inverse, which is now also symmetric about the line y equals x. If I could draw, right? Right, y is equal to that. Whereas this one is x equals. So Bertram, does what it does what do what? So, like I said, most teachers kind of do the most teachers do the changing of variables at the front end, but they call it swapping. So they swap the variables. But why do you swap the variables? Well, in actuality, it's because it's a function, and you want to find its inverse. So you're trying to change. See, for yours, let's see. So here's the other thing, is that all of the properties of the original function and the new function are going to change all of their x's for y's. Okay. So Killer King, the problem here is that the output that you're setting equal to in the middle is different from the two different perspectives. So G input equals output 1, whereas G inverse of output 1 is actually input, right? Is equal to the input. Okay, so let's look at this one real quick. You have an x-intercept of 4, 0. You have a vertical asymptote where the denominator is equal to 0. So that's going to be bring a 2 over and divide by 8. So that's going to be negative 1/4 x equals negative 1/4. You have a y-intercept where x is equal to 0. So that's going to be negative 4 over 2 is 0, comma, negative 2. And you have a horizontal asymptote. In this case, because the degrees at the top and bottom are the same, it's going to be the ratio of their coefficients. So that's 1/8. So now, if you want the properties of the inverse, once you get it all worked out and changed around and all that, you should have an x-intercept of -2, 0, vertical asymptote of x equals +1/8, y-intercept of 0, 4, and horizontal asymptote of y equals -1/4. Right, because all of our x's and y's change place. So okay, I think this should be it as well. So with a -2 factor, this is going to cause x plus 2 to have a -4 value up top, cool, and a -1 down bottom gets us a y-intercept of 0, 4. Okay, cool. Yeah, which is then going to get -2x minus 4 if you multiply it out instead. What does it say? Oh, yeah, that's fine. Yeah. So what it did was it took the negative that I put in front of the 2 and put it down bottom instead. So it flopped the 8x minus 1, it let it be 1 minus 8x. So it just went backwards. Yep, nice. All right. Yeah, Wolfram likes to do an extra bunch of work. No wonder it takes so long. Took like 10 whole seconds just to get an answer to a simple problem. Oh no. What happened? Taylor expansion at square root 26 is real easy. Start at the square root of 25. Yes, so that one is correct because what we can do is rearrange what we've got here. We could say that instead of -2 up top, we put a 2 up top and then x plus 2, and then put the negative down bottom with parentheses 8x minus 1, which then gives us -8x plus 1, and then this is commutative, right? So addition is commutative. You can just swap them. So 1 minus 8x is going to be your denominator now. I don't like the way it looks. And your teacher might be like, did you use an automatic solver to get this? Hopefully you didn't do that. But anyway. Oh my god, I busted so many of my students for using Wolfram or Photomath or Mathway or Symbolab or anything. Oh, so terrible. So, like, I let them use Desmos, but Desmos doesn't give them a step-by-step solution. It just gives them, like, the final answer, which is the same their calculator would do, really, and, like, a few other things, but it's the kind of work that they show. Oh, Megalomorph. Let me tell you. Hang on. Let me pull one up, because this is good. All right. Let's see. Photomath, history. There we go. Yeah, Wolfram Alpha, you have to pay for it, but again, it's one of those things. I can tell when it's the student or it's like, no, this is not your work. All right, so this was f of x is equal to 6x to the fourth minus x cubed plus 94x squared minus 16x minus 32. Find all zeros. Right? So, step one. Oop, nope, wrong one. 6x to the fourth minus 3, x to the third plus 94x squared minus 16x minus 32. Good, right? Everybody happy? Yeah, use the quartic formula. Good lord. There's not enough space on the exam for the quartic formula, I can just tell you that right now. Yeah, no. Anyway, yes. So the way that I teach it in class is step one, you don't actually have to do like the full expansion and do all of the rational roots, right? So what I want, and on the unit exam, I will actually ask them, show me all possible rational roots, right? Like, give me the list that we came up with in class. I did that on the unit exam, not for the final. It's just, it kind of takes too long. So what I do is I tell them, use your calculator. Go 6x to the fourth minus x cubed plus 94x squared minus 16x minus 32. Now, again, you could do it on Desmos or whatever. It doesn't matter. So, what we get... Yeah, I tend to do that. Oh, rational roots theorem. Yeah, okay. What you get for this particular graph. Let's do something that looks at least somewhat okay. All right, what you get for your graph is something that looks roughly like this, and then we've got -1, -2, and 1 and 2, something that roughly speaking goes like this. All right, -1, +1. So that's it. That's all you get. So, naturally, what do you want to do? Well, if you're going to do rational roots, you're going to come in here and you're going to say, all right, this is going to be factors of 32 over the factors of 6. So, what should students do? They go, all right, that's 1, 2, 4, 8, 16, 32, divided by 1, 2, 3, 6, plus minus. What are some reasonable ones? Well, negative a half looks pretty good. Positive like 2/3 looks pretty good. Yeah, don't really have a whole lot else, right? Because everything else is over 1 or can simplify to something else. So, yeah, that's about it. Right? Anybody see anything else? So, again, between 0 and 1, and it's further than a half. This one looks pretty much right smack dab in the middle at negative a half. Pretty reasonably, anyway. And again, there's no other formulation here for something that's going to get you, like, nice, close values to these. So, like, this is it. If it's going to be rational, it's going to be these things. What are they supposed to do? They're supposed to come over and say, okay, let's do synthetic division. Or long division if they really want, but whatever, it's fine. All right, not only, right, the reason that we do this is that not only does it prove that this is a 0, but it also factors it out for them. So it automatically factors. So 6, negative 1, 94, negative 16, negative 32, 6, negative 3, negative 4, positive 2, 96, negative 48, there we go, negative 64, and positive 32, makes 0. Okay, now that we've done that, you can say that we now have a factor of x plus a half that's being taken out. I don't want that. I want this to be a whole number, just generally speaking. So I'm going to take 2 out from all of this stuff and give it to that other thing. So what does that make? That's 3, negative 2, 48. Yep, it's the same thing as the ones above, and negative 32. Right, literally the same numbers as these, just opposite signs. Yeah, it's polynomial division. Yes. Okay, so, right, if you weren't in the US system, this is basically just taking all of our coefficients and just writing them. So, polynomial long division, right? You do 6x the fourth minus x the third plus 94x squared plus, all right, that's enough. We don't need to actually show it. And then this would be 2x plus 1 would be divided in. So what do you do? Okay, we say, looking at the first number, we say, how many times does this go into that? We can divide it in 3 times, and then x can be divided in x cubed times. It's right there, right? The 3. It's right there. And then we say, okay, when we multiply this stuff, it's 3x cubed times what we literally just wrote down or got it from. So, of course, it's going to be 6x to the fourth, right? That's the whole point. And then the next term over, it's not a square root. Square root has a spike and then nothing in front of it. This is a division symbol. All right. And then anyway, this thing times the 1 gets us a positive 3x cubed. And then we subtract. When we subtract, this of course becomes 0 because it's engineered to be that way. And then over here, we say this is going to be a negative 1 minus 3. So then that's going to be negative 4 x to the third. All right, and then what do we do? It's the same thing. How do we get up to negative 4? From a 2, we've got to multiply by a negative 2. Right, and then we need an x squared to get up to x to the third. Well, yeah, that was the next one down, so of course it's going to be 1 degree lower than the previous one and all that. And the other thing is that in all of these cases, we keep subtracting stuff. So we're changing the sign on this thing right here. What we've done in synthetic division up here is said x is equal to -1/2. So when we do that, we are going to come over here. We're going to multiply by whatever number we had here to begin with, which is, again, sort of what we're doing here. We're multiplying by -1/2 to get this term once this negative has been brought in. So we multiply our 6, the previous coefficient, by -1/2, and we get -3. And then we just add going straight down. So -1 plus -3 gets us -4. Well, it's the same thing as over here. And then here, again, we have to say we're going to multiply by -1/2 to get us the 2, which is actually part of our the quotient at the end here. Yeah. So it's a really massive shortcut, and you don't have to take up this amount of space to do the same division as I just did in this amount of space. Yeah, that's also true. I just don't like it. Yeah, the other pattern that I recognized pretty quickly when I started doing this in 10th grade was because this 2 here, it really messes stuff up. So you always end up with a common factor, which then you can pull out and then multiply it in to create integer coefficients. All right, so anyway, then we take this thing, and we've got now 3x cubed minus 2x squared plus 48x minus 32, and now we take out the 2/3 in the same way. So that's going to be unfortunate. So normally I would actually just write this going straight down. You know what? Let's do something like this. We'll do a side-by-side comparison with these things. Oh, foul. Yeah. Side by side. Okay. So then normally what I'd do is I'd say I'm going to do this here, which is going to be x equals, again, 2/3. Yes. So as long as it divides evenly and you get a 0 remainder, then that's going to be a root for it. This is also part of the remainder theorem. Which says that the remainder of p of x divided by x minus a is going to be equal to, that's awful notation, don't do that. The remainder of p of x divided by x minus a will be equal to p of a. So because the remainder is 0, then p of a will be 0 for that particular value, -1/2. And also 2/3 now that we're going to do this one as well. So you can actually, with synthetic division, you can start stringing these and saying like, okay, I'm going to divide by this thing and get this. Then I'm going to divide this by that thing and get what's on the next step. So the 3 comes down. Multiply by 2/3, that's going to get us 2. Add straight down, we get 0. Multiply up, we get 0. Add straight down, we get 48. Multiply up, we get 32. And add down, we get 0. So then we get the same problem that we did earlier. We want this to be now, instead of x minus 2/3, we want this to be a whole number. So let's multiply by 3, which means factoring it out from this term. So that's going to be now 1016. Again, remainder 0, so this is our constant term, which means this is an x, which means this is an x squared. So we have x squared plus 16 multiplied by 3x minus 2. Sorry, I'm kind of ignoring you while I do this thing real quick. Times 2x plus 1. All right, from the above stuff. Right, there should be 2 real roots. We don't know if they're rational or not. We've just proven that they're rational, and they are these numbers, negative 1/2, positive 2/3. And now we have a factored polynomial. We know it's fourth, well, it started out as 4th degree. Now we have 2 zeros that have been taken out, so now we have 2 left over. And then now we can say, oh, what are the zeros here? Well, you could do the, again, just in your head, you can be like, all right, well, this is the zero product property. So at least one of these things needs to be 0. If it's this one, well, we already get the answer we had up above. If it's this one, we get that answer here. If it's this one, now this becomes interesting. What if x squared plus 16 is equal to 0? All right, so x squared is equal to negative 16. So then the absolute value of x is equal to the square root of negative 16. And now we start saying, okay, well, this is going to be I times square root of 16, which is equal to 4i. And yes, so 4i is going to be the absolute value of x, which in terms of the numbers that we have here, x is going to be plus or minus 4i. Or the 2 from above. So, well, might as well, I guess. So plus or minus 4i, negative 1/2, and 2/3, or 2/3. All right, so let's see what I've been missing. Okay, so Killer King, we can string them both together. We could start over, right? And plenty of my students do that. You can start over all as much as you want. The point is that I don't need to just test them. Really what I need to do is test them, but also, prove in a mathematical sense, in a loose mathematical sense, I'm going to prove that these are in fact zeros. But also, this is helping me to factor this polynomial. So if I can factor this polynomial, now it leaves me with the part that has non-real answers, right? The ones I can't find. And in fact, it could be any irrational value, whether it be complex non-real or mixed complex or just an irrational real. If you ended up with something like, x squared plus 7x minus 5, right? That's not going to come out with a nice number. It doesn't have nice zeros. So that took me about a quarter of a second to make sure I didn't hit the wrong number. So yeah, it'll also say, okay, now that I've factored it, now I can find the other ones by using the quadratic formula. And of course, you could also do that here. We don't need to because it's just a simple square root. I'm not there. There we go. So yeah, this one's a simple square root, so we just make it plus or minus 4i. That's easy enough. And then we have the other two. Okay, so I've distracted enough. I have distracted myself enough. This is what students are supposed to do, right? So if I ever do that, that is me placing it in the wrong location. Not because this is multiplication, but because I was quickly going through and did not spend the time to bring it down here and make it obvious that it was a decimal. However, I actually do agree with you Europeans out there. I'm pretty sure that this would be a lot more convenient to place in the location for the decimal value to say, okay, here's what separates um, here's what separates our whole numbers from our fractional numbers. So I think putting a comma in would be a lot better. It's never going to happen because just like miles versus kilometers, we're not going to switch to metric anytime soon. We're never going to switch this. It's never going to happen. And, you know, something like 5,689,686, right? I'm making up a number here. Right? Putting commas in here is useless. These are big, giant things that would like be much better served, right? $5,689,686.87. Look at this ridiculous thing, right? Putting the commas in here would be much more obvious to go the other way. So 5,689,686 and 87 hundredths. Makes way more sense to do this because this is bold and obvious. This stuff, you can easily just mistake it for not being there. Anyway, that's enough of my ranting. All right, whoa. There we go. All right, so what do students do? All right, the ones who are totally not cheating, and how dare I make that assumption, do something like this. There you go. Everybody get that? And I go, okay, how'd you get 2x plus 1? And they're like, I'm like, okay, here's another one. Do it again. And usually they're like, So the best liars have said, well, you know, I used photomath to learn that way, but then I didn't use it on the exam. Yes, it's perfectly correct. It's just stupid. Like first of all, you'd never do this. What are you going to move? You're going to move the A value to the other side and make it negative? That's like the one thing that I told you is just a ridiculous thing to do. Yes, oh yes, using photomath on the exam. Now keep in mind, most of them, for this class, you know, this semester, last semester especially, and the semester before that, they were home. So like they have to do a scan with their, you know, with their they have to do a scan with their webcam and show that they don't have anybody around them. They don't have other people in the area, whatever. But I mean, they got their phone right there because it's or like it's over on the side where the webcam's not gonna see it. Um, yeah. So really, what this really is they're taking 2x plus 1 and it's dividing 2x plus 1 out from the whole thing. And so it's a division algorithm, right? It's more or less like this thing over here. It's the division algorithm. But yeah, they're just grouping terms. But like, come on, guys. First of all, right, it's got literally the same steps as what I have on PhotoMath. Secondly, right, you're making the A value negative, which I told you is a ridiculous and stupid thing to do. And then thirdly, you're doing something that you can't even explain. Like, come on. Now, would I ever do something like that? No. Goodness, no. So, like, what they're essentially doing is, like, coming up with 6x to the fourth minus x to the third. And they're saying, all right, this is going to be, if we know ahead of time, right, that 2x plus 1 should be a factor, which, again, if you're paying attention, you know that 2x plus 1 should be a factor. So we're saying, okay, if 2x plus 1 is a factor, how many times can we divide it out? Well, if you have 6x to the fourth, then it's going to be 3x cubed. And then we're going to have 2x plus 1. Okay, what does that mean? Well, from above, we should have had a plus 3x to the third. Now, in order to get a negative 1 here, that should be a minus 4x to the third, in order to get that thing back. So now we've got minus 4x to the third plus some number of x squareds, which again, this is going to be a minus 2 2x plus 1, and actually that's an x squared, right? Minus 2x squared, 2x plus 1. So then minus 2 times positive 1 needs to be a negative 2 in order to make that work, which means that this is going to have to be a plus 96 x squared. And then we continue from that. Yeah, you have to come up with all of this stuff. Like, where did it come from? And they're just like, it's fine. Okay, give me 1 minute here. Yeah, so like, we actually do some of this in Calc 2, which is kind of interesting. When you start looking at like, damn, what was it? Well, U substitutions sometimes, and like, trying to think of where else I use this. U substitutions and partial fractions. There we go. That's the name of it. It's like when you do partial fractions, sometimes there's something like that. Like, you're doing x plus 4 divided by 3x plus 1, 2x minus 7. you want to be able to split this into a over 3x plus 1 plus b over 2x minus 7. You could start like throwing around a few different things in terms of like, if one of these was going to divide nicely into the top. Maybe I'm doing that wrong. I can't think of a good example right now, but anyway, sorry. Totally guessed and verified, yeah. So I mean, like, plus and minus 4i actually was something that we were encouraged to take a guess at when we were in high school, like in my class. Again, it's a ridiculous idea. Why would you want to do that? And then you could, again, I tell my students, and I was told that you need to then factor this out and actually do like synthetic division to prove that it works. I think actually when I was doing synthetic division, we were told to, basically do the whole thing where you start over again and just like verify that one thing rather than factor out, at least at first. I don't know. It's been 20 plus years, so that's no. So if I want to plug in negative a half into the function, yes, that is just guessing and checking. It doesn't get you anything other than proving that that one number happens to work. But I tell my students, like, you need to show, you need to find all of the values. So just plugging a number in doesn't really get you anywhere. It says like, yeah, that's a 0, but okay. If they plug in all 4 numbers and just magically happen to come up with them, that's not good enough for me. I'm not gonna, no. Yeah, I give them like a point for the fact that they found answers, but most likely they didn't find the answers. Let's be honest. Still didn't find this one. Okay. So, yeah. The number of gifts that you would receive if you were talking about the 12 days of Christmas, as we were doing up above, where every day you get uh, one additional gift of the next integer value up, and then all of the previous gifts as well. This is again going to be uh, n times n plus 1 times n plus 2 all over 6, which we can divide the 12 by 6 and get 2, and then 13 and 14 are going to be the next two numbers. And then this gets us 169, 182 times 2 is going to be 364, right? Yeah, 364. I mean, most of the time I just tell them that, computer or calculator or whatever is only as good as the user. And then I'm going to next semester, definitely point this example out and be like, see this? This person cheated. I'm definitely not going to use someone's actual exam, right? That's wrong on so many levels. Um, but I will most definitely uh, pull this out and say, okay, see this? I know that if you have this, that you use this app or one very similar to it. Woo! Yeah, only off by 1 1/4. Oh, did I just blur myself? Yeah, that's all right. uh, yeah, there's all sorts of stuff that students try to get away with. It's just like you don't even know how wrong it is to try to do this. Apart from the fact that they're, just blatantly cheating, which is not cool. Right? These are breaking the terms and conditions of what we had decided to agree on here. Uh, Now, perhaps they didn't necessarily consent to all those rules, but they did sign the front of the page that said, "I promise not to use any of these apps." I never agreed to anything. That's funny. I've got your signature right here. Everybody just clicks "I agree." Pfft, that doesn't count. Oh man. Did you all see the what was it? And whatever company that is. Hang on. I'll pull it up. Yeah. This Nega Oryx retweeted something that like one of these companies put out. It was under duress. Yeah, NZXT. There we go. Whew. NZXT announced their partner program, and a whole bunch of people read the fine print. And it says, in exchange for being an NZXT partner, you hereby grant NZXT a perpetual, non-exclusive, transferable, sublicensable, irrevocable, worldwide, and royalty-free license to publish and display your content in whole or in part in any medium for any business purpose. And a few people are like, oh, that's interesting. Yes. And yeah, yeah, that their entire page, like just attached to that particular thing, is a whole bunch of people who have taken that, clipped it, and just posted it and been like, "That is really crappy," and how dare you? Whew. I'm so glad I'm not going to make money off of this. It's just obviates the whole problem. Anyway. Yeah, yeah. No, I can't do that. So Matthew, the who's it's um entrance exam, our placement exam is supposed to do that. And if they score a certain level on any given thing, they're allowed to take whatever class it is. Now, that means that they could have understood some of the calculus questions and gotten some decent points toward their placement. But then they don't understand, let's say, how to solve higher degree polynomials, or they don't understand at all how to do inverse functions, or they don't understand how to do sums and sequences, right? But they have some other random stuff that's getting them enough points to qualify for. Well, if it's that bad, they'll qualify for like the um, uh, accelerated version of pre-calc, which is the one I'm teaching, which is a 5 credit class. So you're expected to do 5 hours of class per week, which, as many teachers have probably told you all, if you do 1 hour of class, you should do at least 2 hours of outside stuff for class, whether that be for actual class or class work or homework or whatever. So, like a 5 credit hour class, you should be doing at least 10 hours of prep and or homework every single week. Yeah. I mean, 3 hours, or yeah, 2 extra hours of not listening to my voice, um, but still doing math. Yeah, so that's an issue, Matthew, is that there are a lot of students for whom my class is the terminal class. Um, Not this one in particular, because the accelerated one is pretty much only used for people who need to go into calculus. There are some people who are like, I'm just going to take this because I need like a certain number of credit hours or whatever, and it's like you shouldn't be torturing yourself. Um, so like poll on the first day of class, right? Hands up poll. How many of you are going on to calculus? Every single student should be raising their hands. Um, this is a 2-year college class, so the students who are here, some of them are 2-degree terminal, so they're just going to be here for their associates, and that's it. They're going to go out into the workplace and do whatever, and then they may or may not at some future date do further college work, but that's you know not really it's not really my place to dictate to them what to do, right? It's they're going to basically do what they need to do to get the associates and then move on. They're just going to go to their work wherever that is. A lot of our students actually come to our 2-year college because we have a good program and it's cheap. And like our program specifically is almost as good as our flagship university, depending on what it is that we're talking about. In some cases, we might actually be better because the flagship university might not have a very good program in this one little area. So, like, I went to the University of New Hampshire. The University of New Hampshire is very well known for its nursing, business, and nursing and business programs. Um, Maybe liberal arts, just to get whatever degree you just want to get and move on. But it's best known for nursing and business. And so if you're there for one of those two programs, you know you're going to get like a really quality education, and like everybody's really into it. Everybody's really into like doing those things, and it has a high reputation among businesses out in the state. What they're less well known for is their like math, engineering, physics, STEM just generally. Nowadays, it's actually a bit better than it used to be, um, owing at least in part to the work of Yitang Zhang, who you may know him, those of you who have studied some math research. He was the guy who put his foot in the door to solve the twin prime conjecture. Now, he didn't actually solve it, and I don't think it's actually technically completed yet, but the group that was working on it after him based all of their stuff on his research, and like he got a big name, he moved to a different college, he did all sorts of stuff. So like the University of New Hampshire got kind of a boost from that. Yeah, so the prime, he realized that it was possible to say, well, there are an infinite number of twin primes whose distance apart from each other is 70 million. So he was able to prove that. And then everybody else in the whole place was like, that is a completely different approach than I thought we were going to take on this. Let's try to improve that. So then they shrunk the prime gap to, I don't know, 4, something like that. Maybe. I haven't really looked at the research in a couple of years at least. Um, but yeah, the gap was shrunk from 70 million down to a fairly substantially small number. Still bigger than 2, I believe, but so yeah, University of New Hampshire was slightly better known for its math program after that. hmm Mm. I'm gonna trust Terry Tao on that one. I actually had Dr. Zhang for my proofs class, and I stopped showing up. This was a terrible thing. I stopped showing up after 2 months because it was an 8 a.m. class, and I got mono. And stupidly, I didn't ask somebody, hey, he also has a 10 a.m. class. Do you think I could switch because of like, medical concern? No, I didn't ask. I just stopped coming, and that was a terrible idea. I should have. So let this be a lesson to anybody out there. Extenuating circumstances exist. You are potentially allowed to do something that like normally you would never be allowed to do. So, you know, this last couple of years, people are like, "Hey, I've got COVID, so like, could I be given a little leniency on this, or can I drop, or can I withdraw from the class like way after the withdraw date?" And the answer typically has been, yeah, it's fine. Just do your thing. Come back next semester. Give them a medical withdrawal, and everything's fine. Um, yeah. Yes, also bad idea for relationships. Good lord. Oh, goodness. Yeah, my spouse had one of those, or actually had 2 of those. It's like these exes who just ghosted her. Like, how does that happen? And incredibly, talking like if you know her, like, why? How? How did they just stop? Don't have the guts to just speak up and say something. And no, okay, just never talk to you again. All right, all right, Matthew. Have a good night. See you later. um, I mean, we did one Christmas problem, so that's cool. Anyway, if anybody has any more questions, let me know. Um, so otherwise, we have a couple of people we can go out and raid. The guy I usually raid here is Jason Charles Miller, who does Whatever You Want Wednesdays. I mean, I did other stuff, right? But who does? He's a musician, rocker. He worked for Geek and Sundry, and oh, that was what I also wanted to do here, right? The famous problem that probably everybody's already heard of, already seen, but this is a fun one for somebody made up something as far as what this was. I don't remember exactly what. Yeah, I love JCM's music. As much as I do like the pretzel stuff that's going on in the background here, I do much prefer his. um, yeah, the volume of pizza thing. So this is a fun one that like uh there was another one. I've got it somewhere. It's probably in my bag. I'm not gonna not gonna dig it out. But yeah, this is one of those like if you play around with this, it just comes out to something rather nice. So uh the r squared y is equal to x over m minus sa multiply by m on both sides. So, all right, and Megalomorph had the how was Halloween equivalent to Christmas. So this one was October 31st. It's equivalent to December 25th. Where if you're looking at this in terms of number systems rather than the months specifically, this is decimal, so decimal 25 is equivalent to octal 31. So in octal, this is 3 times 8 plus 1 times 8 to the 0. So here, this is going to be 24 plus 1 in decimal, which is equal to 25. So, yeah, I really like playing around with other number systems. You know, oh man, I got so screwed up a few months ago. Somebody was like, oh, it's October. I was like, it's the 10th of October, 2021. And I wrote down 8/10/2021 because oct means 8. And then I just had a moment where I was like, oh no, that is not what I meant. Why do we do this to ourselves? December, dec. December means 10. I was like, why? Oh, man. Yep. I was like, we should just fix all of it so it's back to normal. Normal. And then it no longer aligns with the numbers, so like, what the hell, man? Ugh, lousy smarch weather. Yeah, and of course they give them the summer months, the ones that were nice, because those are the ones they wanted to pick for them, for themselves, or for the in honor of the emperors, not the ones in the freezing months. Touche. This is like that old red versus blue joke. Yeah. The alien says blarg, and the guy's like, wait, does blarg mean yes? Blarg. Yeah! All right. Well, good evening, everyone. Hope everybody has a good Christmas, holiday, New Year, whatever it is you're doing, or nothing at all. If you happen to not celebrate anything in particular, I just hope you have a good time. Did I get my photos printed? What photos? uh, Now I'm really confused. Alien photos. What did I do? Oh, I'm committed, alright. Alright, anyway, I'm going to start a raid over at JCM's channel. So thank you everybody for coming in. Yeah, this Friday I'm probably going to pass because, you know, Christmas Eve and all that. Um,